Yeah, I know it. All right. Let's jump in. So today we're going to put it all together, mostly all together. We're going to cover the rest of the statistical thermodynamic functions, where we're going to calculate the energy, entropy, enthalpy, Helmholtz free energy, and Gibbs free energy. I went ahead and included the Helmholtz and the enthalpy and stuff today to kind of get a jump on the rest of the week. So there's going to be a fair bit of changes in the notes today, and the one in your notes, I'll show you the differences. So there are going to be some notation differences. So I want you to correct your notes and do the problem like we do it today. Okay. So once again, though, if you're dealing with the high temperature limit or moles of molecules, you can jump right to the equal partition of energy, where these would be for a gas phase molecule, the internal energy for translation, rotation, and vibration would be calculated using these simple formulas. But today we're going to use the counting formula, where we actually do the summation and calculate the partition function, and then turn that energy level diagram into an average energy. Let me go ahead and add, I've shown this in previous lectures, but remember this piece right here is the probability of being in state I. So this simplifies again to that sum of each energy times the probability of being in that energy state. So if you have an energy level diagram with I, 0, 1, and 2, then there'd be the probability of being in each one of those states times the energy of each of those states, added all together, and that's your average energy. So this is USHAG. We asked last time, what is USHAG? Yes? Okay, yeah, sure. Okay. Okay, so USHAG, that's the internal energy is U, the entropy is S, enthalpy is H, and that Helmholtz energy is A, and then Gibbs energy is G. Now notice these are not deltas. When we do reactions, then we get to deltas, like delta H and delta G and those kinds of things. So these are just the energetic functions themselves. Then if we wanted to analyze, say if there was a change, we could calculate delta G and determine if that change was spontaneous, right? So do you remember from your earlier chemistry classes what delta G and spontaneity have to do with each other? Yeah, when delta G is negative, then the reaction as it's written is spontaneous. If you flip the direction of the reaction, you flip the sign on G. So okay, so I'm going to scoot forward. We'll see these equations again. All right, so let's consider this problem. It's the same problem as the one in your notes, except everything's in wave numbers instead of temperature of Kelvin. So, in fact, the math is even the same. But so the energy level diagram is shown here, and we get this from the problem. So it says, consider a system of particles having 3 non-degenerate energy levels separated by an energy of 200 wave numbers. So one of the skills in PChem is being able to take this text and turn it into this energy level diagram. So look at how it was written. The usage of these words. You've got 3 energy levels here. It's telling you that they're non-degenerate, and it's telling that each of the levels is separated by 200 wave numbers. So now you see how we constructed this. We put one at 0, one at 200, and one at 400, because that's the separation between all 3 energy levels. So hopefully that's something within your range of abilities. If not, study the way this is written and see that, you know, that you could calculate this kind of energy level diagram. Okay, the way I do these problems, I think the easiest way to do these problems is when you're calculating the partition function, to do it in a table format. Okay, and so if we wanted to label these quantum states with the quantum number I, we would have, you know, 0, 1, and 2. So the ground state I equals 0 has 0 wave numbers of energy. The first excited state has 200 wave numbers of energy. The second excited state has 400 wave numbers of energy. They're non-degenerate, so the G of I's are all 1. And so then this Boltzmann factor here is just that exponential piece, e to the minus EI over KT. So that first one is going to be 0.14, or the top one will be, and then the next one 0.38, and the next one 1. Let me just show the math for this one. So that's e to the minus 400. And remember that KT at room temperature is equal to about 200 wave numbers. So this would be 400 over 200.
So when you're doing problems, do you want us to use 200 or do you want us to use more exact?
207, 200 is fine. Yeah, just to show me, because you'll be able to show me that you know what you're doing, you know, with the 200. And if it's simple, like this, it makes it much simpler, because this is just then e to the minus 2. Yeah. And then this one was e to the minus 1, or 0.38, and the bottom was e to the minus 0. So then we sum all of those Boltzmann factors together, and we get 1.53. Okay. So that's our partition function. And help me interpret the partition function. So what is it account of? Realizing that when everything's in the ground state, the partition function is 1. So at absolute 0, it collapses down to 1. In this case, at a billion degrees, Q would be 3. Okay. And so what do you think Q is telling us? This is, again, an interpretive piece of Q. We've talked about it a bunch of times in class. It's similar to that. It's think about it. If everything's populated at equal probability at really high temperatures, the maximum for this particular energy level system would be the Q of 3, because every at really, really high temperatures, this piece right here, if temperature goes all the way up very high, this piece approaches 0, and e to the 0 is 1, and so it'd be 1, 1, and 1. So Q would add up to 3. That's super high temperatures. At super low temperatures, this would be e to the minus a huge value. So this would be very small. This would be very small, but this would be e to the 0. So it'd be 1. And so we would, at low temperatures, Q would equal 1. And this particular energy level system, at high temperatures, Q would equal 3. So what is Q keeping track of? And why is it named the partition function? What does the word partition mean? There's another word. It's a synonym for partition. Like just in furniture, what does a partition do? It divides the room. Okay. And the partition function is dividing the molecules into what? Where they are, how many energy levels there are. And so at really cold temperatures, there's no division of the molecules. They're all in the ground state. at super high temperature, and since this energy level diagram maxes out at 3 levels, the maximum partition function would be 3. And it's divided among 3 energy levels. So it's telling us how many energy levels are populated. It's a sort of an estimate. So right now we have an estimate that 1.5 energy levels are populated. I'm just trying to give you a feel for what the partition function means, how you could interpret it. And remember, the translational partition function for argon at 1 atmosphere at room temperature was 10 to the 30. So it has 10 to the 30 energy levels populated in a single, gaseous molecule bouncing around in a room. Okay. So let's go on to calculate the internal energy. So remember, the internal energy was those probabilities times the energy function. So here we have the probabilities. So this is roughly 10%, or 0.14 divided by 1.5. The next one's 25%, 0.38 divided by 1.5. And then the last one is the balance, 66%, 1 over 1.5. So those are our probabilities. So this is 66% here, 25%, and 10%. Okay, so very little population in that top level. Now, think about the average energy. So we have 10% of the molecules with an energy of 400 wave numbers. Okay, so that's, it's I'm using my calculator, so it's not exactly 440, but it's 38. And then 25% of the molecules have an energy of 200. And so you're adding those up, and then you have 66% of the molecules, but they have an energy of 0. Okay, so they contribute nothing to the average energy. They actually drag it down a little bit. Does that make sense? Yeah. So 66% of the molecules have 0 energy, and so our average energy is going to be 87 or 88 wave numbers. So that's kind of interesting. Right here is our average energy. And I always think it's kind of interesting. This is definitely a situation where you have quantum effects, right? We only have 3 levels. And the average energy is 88 wave numbers. But there's not any molecule in this system or any particle in this system that has that energy. That's the average of the whole system. So it's kind of weird if you think about it. If you've got these particles in a bag and you pull one out, you're going to get one at 400 wave numbers. It's a hot one. You reach in, you pull out one that's got 0 wave numbers. You pull one out, maybe you get one that's 200 wave numbers. You'll never get one out of the bag that has 88 wave numbers of energy. That's just the average of the whole system. Now, if we did that, we were pulling all of these molecules out, and let's say we got 80% of them, what we pulled out were 400 wave numbers. We would say that doesn't match the Boltzmann distribution for room temperature. And so we would say this system's not at thermal equilibrium. So this is what defines thermal equilibrium. When that system comes to thermal equilibrium, it will have this population. If it's not at thermal equilibrium, it won't. And so we use these Boltzmann calculations to define what we mean by thermal equilibrium. So the electrons in this tube lights, they're emitting light, which is, again, a very hot situation. So 700 wave number light coming out of something, if it was in thermal equilibrium, for it to produce that amount of light at 700 weight numbers, it would need to be like a 20,000 Kelvin. And those lights, the glass, if it's Pyrex, melts at 500 Kelvin. Or is it 500 C? I think it's 500 C. But the point is, if the light was coming from black body radiation in those tube lights, in other words, thermal equilibrium system, there's no way Pyrex would survive that. It would melt. So that's really weird. How are we getting light out of something that's not at, 6,500 Kelvin? And the point is, it's not at thermal equilibrium. We're pumping electricity through the mercury vapor. And so the electrons are emitting light as if they're at 6,500 Kelvin. But translationally, those mercury atoms are only have the translational energy of, I don't know, maybe if you touched them with your hand, they'd be warm. They wouldn't be super hot. So, they might be, 80. Let's see, I'm probably thinking about 90, maybe 100 Fahrenheit, just like a warm object sitting in the sun. So that's an example of a system that's not at thermal equilibrium. The electronic temperature, about 6,500 Kelvin. That's why it's giving us the light that it's giving us. But the translational motion, rotational motion, which doesn't apply to mercury atoms, so translational motion is only at about, I'm trying to convert from 100 Fahrenheit to Kelvin, and I'm not getting it. But if you touch it, it's about 100 Fahrenheit. It's just warm to the touch. Okay, let's talk about entropy. So from our statistics chapter, we've talked about the various configurations and permutations, and you could calculate statistical weighting factors for those situations. And so that's what this W is. That's the statistical weighting factor. For various permutations or configurations. And the natural log of those weighting factors times this constant, K, which turned out to be Boltzmann's constant, was the definition of entropy. And this equation was so successful that Boltzmann put it, or his family, or whoever did this, the foundation honoring him, put it on his tombstone. So that's pretty cool. I mean, this is his gravestone, and he's got the entropy equation on his tombstone. Taking into account those weighting factors and Avogadro's number, eventually became this partition function. Okay, and so now this is the equation that we're going to use, and we're going to ignore this extra constant, and we're just going to calculate it with this. So the internal energy over temperature plus Avogadro's number times Boltzmann's constant gives us the gas constant. Let me just show you that real quick. So K is equal to 1.38 times 10 to the minus 23rd joules per Kelvin. And Avogadro's number is 6.022 times 10 to the 23rd per mole. If you multiply those by each other, you get this number, 8.314 joules per mole Kelvin. So you've been using Boltzmann's constant this whole time. You've just been using the molar version of it. And so here's a younger picture of Boltzmann. Okay. One of my favorite scientists. Okay, so let's look at this same problem that we've been working on, and let's calculate the average entropy at room temperature. So here was our internal energy in wave numbers, 87.9 wave numbers, and here's our equation for the entropy. And so we're going to put these all together. And the one thing that I want to point out here that catches people and I always get an email every year during this time for the homework. They're like, I don't understand because R and, I get the wrong answer on Blackboard and so on. But whatever your energy is, R must match. Okay. So in this case, we've got an internal energy of 87.9 wave numbers. And then we're going to divide by Kelvin. So we need to match these two. And so R must match those units. So we would not use 8.31 for joules per mole Kelvin, okay, because those are the wrong units. Okay, so what do we do for wave numbers? Well, K over HC is equal to 0.695 wave numbers per Kelvin. And so since our internal energy is in wave numbers, we're going to use this version of R, the Boltzmann's constant over HC, 0.695 wave numbers per Kelvin. So that way our units in both pieces of the sum work together, they're compatible. Okay. And then the natural log of the partition function. So here we are, these are the two pieces, 0.295 from the first piece, 0.294 from the second piece. We get 0.589 wave numbers per Kelvin. So that's our entropy for this system. Any questions on this one? Okay. So here's the internal energy and the entropy. Let's calculate the enthalpy. Okay. So here's the enthalpy equation. We don't need the entropy for this one. But again, we've got to make the decision on which R to use. And so we have the internal energy here. So again, R and U must match. So since our internal energy is in wave numbers, then we use the 0.695 wave numbers per Kelvin times the temperature. So here's our enthalpy, 295 wave numbers. So this is the total amount of heat that's available in the system. Another way to think of it. I'm just going slow since y'all have to do a lot of writing. Okay, next let's calculate the Helmholtz energy. So we have entropy here, the internal energy there, and this is U minus TS. So we have to use both the internal energy and the entropy. So once again, we're going to match the units. We've calculated entropy in terms of wave numbers, our energy in terms of wave numbers, and so this is going to work out just fine. So while y'all are writing that down, let me talk about the Helmholtz energy. So Gibbs energy, it was good job Destiny earlier saying that identifying that negative delta G's were spontaneous. Well, negative delta A's are also spontaneous, but we always use delta G in our academic situations because we have open glassware open to the atmosphere. So when we're refluxing or we're doing some sort of chemical reaction, most of the time in organic chemistry, refluxing at a certain temperature for so many hours and so on, we're not heating a sealed system. It's frowned upon in academics because we're using glassware. Okay, but in chemical engineering and industry, they have stainless steel vessels, and so there you've got a fixed volume and the pressure rises. Okay, so looking at the Helmholtz energy is what you would do at say 30 atmospheres and whatever temperature would this be spontaneous. And so they would use the Helmholtz energy to determine if this reaction is going to go forward. Whereas in academics, most of the time where you're dealing with glassware, containers that may break at high pressure, and so we want to use the Gibbs energy because it would be spontaneity at constant pressure. So that's the difference between Helmholtz energy and Gibbs energy. So here's our answer here, minus 87.5 wave numbers for the Helmholtz energy. Okay, next we'll do the Gibbs energy. I changed it to Gibbs energy, but I didn't change this little red text here, so I'm going to scratch that out. Put Gibbs. And then I'll put this in. Constant pressure spontaneity. And again, that would be for changes in Gibbs or changes in Helmholtz. Right now, we're just dealing with the sort of absolute value of Gibbs energy and absolute value of Helmholtz energy. So H minus TS. So we've got to know the enthalpy before we can calculate the Gibbs energy. So 295 was our enthalpy, and then we have the entropy term. And so we end up with 120 wave numbers of Gibbs energy in this system. So we've calculated USHAG, all of them. The internal energy, the enthalpy, entropy, Gibbs energy, Helmholtz, gone the whole route. And so let's summarize these thermodynamic values. We've done everything in wave numbers. Let's say we wanted to go in terms of joules per mole. So how would we get from wave numbers to joules per mole? Let me review some of the equations. So we have the Planck equation, E equals h nu. And then what's new? This is our little in-class joke. What's new? It's right here, C over lambda. So when somebody's walking across campus and they say, hey, what's new? You say C over lambda. And they go, oh, yeah, you had Williams. Yeah, so what's new? Very good, very good. Okay, so this 1 over lambda, though, if that lambda is in wave numbers, then we call that the frequency in wave numbers. So we also see this tilde here indicates that we've got the wave number value. And so the energy is hc over lambda or hc nu tilde. So we can take our wave number values here and multiply them by Planck's constant and the speed of light in centimeters per second. So doing that to all of these, and then if we wanted it in per mole, then we would multiply by Avogadro's number 2. So this one is going to be in centimeters per second. This one's moles minus 1, and this is joules times seconds. So our seconds cancel, and our centimeters cancel with the wave numbers, and we're left with joules per mole. Okay. And again, even if you didn't, let's say you didn't want to go all the way back to the, these equations, you could just look at the units and say, I've got wave numbers. I've got to get out of wave numbers by using speed of light, and I want to get into joules. So joules from Planck's constant would cancel that per second, and then I've got to get to per mole, so I got to use Avogadro's number. So you can just use the units to guide your math, and it'll work every time. Okay, so we have this 87.9 wave numbers. Multiplied by all of these things, we get 1,052 joules per mole. Okay. And then the entropy, 0.589. Wave numbers per Kelvin times those three, we get 7.04 joules per mole Kelvin. Here's the enthalpy. So 295 wave numbers converted over 3,529 joules per mole. And then the Helmholtz energy, minus 1,047 joules per mole. And then the Gibbs energy, 1,431. Let's go ahead and convert our values here too for our energy level diagram. Of course, this is going to be 0 joules per mole. That's no problem. But what's 200 wave numbers? Let's convert that one over. Okay. So that's about 2,394. 2,394 joules per mole. And twice that times 4,788. So that would be our energy level diagram in joules per mole. And we could have done the whole problem that way. We could have, from the beginning, consider a system of particles having 3 non-degenerate energy levels separated by an energy of 200 wave numbers. We could have converted those 3 wave number values into joules per mole, and then we would have all our values come in with joules per mole, and we would have used the R as 8.314 joules per mole Kelvin here, and we would have done all of those with R being the traditional R that you used. Okay, so you can write these problems in many different ways, and you can do them in many different ways. Okay, I just felt that it was easier if the problem was given in wave numbers to leave my constants like Boltzmann constant in wave numbers, the 0.695 wave numbers per Kelvin, and do them that way. And then if you wanted to, if you were asking me then what are these things in joules per mole, I can convert them all later. Okay, but again, it's like a city block, right? I can go forward 1 block and to the right 3 blocks, or I can go to the right 3 blocks and forward 1 block. It's the same destination, just different ways to get there. So, and in the worked out problems, like if you were to do one of these by hand on the test, I don't care which way you do it, as long as you show me your work and show me your units, and I follow your logic, right? So it's pretty straightforward. Okay, so what would we do then if we had this situation where maybe we had some degeneracy? Okay. So let's calculate this situation. And so if we go back to the, I guess it was early on in the notes. Of course, this one down here is still a Boltzmann factor of 1 because we have e to the minus 0. Okay, this was e to the minus 1 times 2. It was 0.38 times 2. So what is 0.38 times 2? That's 0.76. Okay, so this one is going to be 0.76. That is e to the minus 1 times 2 for this number right there. Okay. And then this was e to the minus 2 times 3. So we'll calculate this one here. Oops, I'm running out of space. Let me erase that. That's this one right here. Was it 0.14? Can you go back and look?
It was.
0.14 times 3. So what is that one? 42? Okay, good job. Okay, let's add those up. So our Q is 8 here. 8, 7, 8, 11. 2.18. Now these were all calculated at room temperature, so the temperature hasn't changed. All we've changed is the degeneracy. Okay. Let's calculate our probabilities. So here we're going to need a calculator. So 0.42 divided by 2.18. 0.193. Okay, and 0.76. 2.18. 9349. And then 2.18, 0.459. And they add up to 1. Okay, that's good. At least, well, okay. So these are our probabilities. So we have up here divided among all three of these levels, 19%. And this one was 35%. And this is 46%. What were the earlier percentages? Can you look at yours?
%, 25, and 66.
Okay. So earlier it was 66%. The middle
25.
one, 25, and 10. Look what degeneracy has done. It's really increased the probability of being excited. It doubled the top one. Okay, so what's our U? Let's calculate this. So it's the energy times each probability. Okay, so 400 wave numbers times 0.193 plus 200 wave numbers times 0.349 plus 0. Doesn't matter what zeros times, it's going to be 0. So 147. So look at what happened to our internal energy. Since we've populated more excited states, our internal energy went up to 147 as opposed to 88. And yet we're at the same temperature. That's the thing. That's the thing that I want you to puzzle over, right? Just because two things are at the same temperature doesn't mean they have the same energy. It depends upon their heat capacity. Okay. The derivative of U with respect to T is what gives us that heat capacity. Okay. And so we're going to have different systems. If we put these in equilibrium with each other, they're going to move, or it'll be spontaneous to move from one to the other. And so that's what we'll do next time, is we'll calculate the rest of the values for this particular system, and then we'll put them in thermal contact with each other and see which direction is spontaneous. Okay, so that's the K piece. We have USHAG and K. K is the equilibrium constant. So to do this full problem, we need to do the USHAG calculations for the products and the USHAG calculations for the reactants, and then do all of the deltas, see if it's spontaneous, and then we can calculate the equilibrium constant. So that's why this goes over 2 lectures. So next time we'll do all of the USHAG for the second system, and then we'll calculate all of the deltas. We'll see if it's exothermic or endothermic. We'll see if it's spontaneous, what we say exergonic or endergonic. That's the Gibbs energy version. And then see what the equilibrium constant is. Okay. All right. So I'll see you next time.